Hello, my name is Ramón Cuadrado and I'm going to talk to you about the spin orbit coupling and more specifically how the spin orbit coupling is implemented in SIESTA. Firstly, I will give you a brief motivation about why is important the use of the spin orbit in your DFT calculations. I will define what it does mean and how it is possible to include the spin orbit in SIESTA by means of the pseudopotential approximation. I will also summarize what the scalar relativistic means compared to a fully relativistic calculation. And finally, I will show you one example of what we can obtain with it. Magnetism, and as a part of it, the inclusion of the spin orbit coupling in the theoretical description of materials, is very important because there are many applications in science in which the spin orbit is fundamental, such as drug delivery, catalytic reactions, magnetic recording, biological sensors, or the fabrication of optoelectronic devices, among others. Let's focus, for example, in the development of new magnetic materials to store information. Several geometric configurations are currently object of research, such as multi-layer materials or nanoparticles supported on surfaces. The main goal is that the stored information has to be stable for years and have to be able to maintain their spins orientations for elevated temperature. If this is achieved, the stored information will be stable and does not disappear. The main bottleneck is that high magnetic anisotropy is needed in those materials, that is, the difference between different self-consistent energy values for different magnetic alignments. So the important thing is that those energy differences can be obtained by means of the inclusion of the spin orbit coupling in our calculations. From a theoretical point of view, if one includes the spin orbit in their simulations, can obtain, for example, the splittings of the band structure that in a common DFT calculation is not possible, since without spin orbit the bands are degenerated, as we can observe in the figure on the left for gold. Also, the bands of any topological insulators can be described correctly, as we see on the right side on the slide for bismuth selenide. What does the spin orbit physically represent? The first thing we have to know is that the spin orbit coupling is a relativistic effect and arises from the interactions between the intrinsic magnetic moment of the electron and the magnetic field seen in its orbital motion around the nucleus. Regarding the Hamiltonian to perform a DFT calculation, we can have two kinds of relativistic approximations. The first one is called a scalar relativistic approximation, in which only the Darwin and velocity correction terms are taken into account. That would be the first two terms in this equation. If we include the spin orbit term, we will have a fully relativistic description of the system as reads in this equation. In the first case, the Hamiltonian matrix is composed of only the diagonal spin up and spin down blocks, having zeros in the off-diagonal blocks. If now the spin orbit coupling is included, the off-diagonal blocks won't be zero, increasing the number of total matrix elements and also mixing the spin up and spin down states, whilst for the polarized case were separated. One significant change in the description of the states is that we will need, instead of LM states, JMJ states, being these last spinors that are two components vectors. Now the next step is to include in the total Hamiltonian of SIESTA the spin orbit coupling. So how we can do it? This is done by means of the pseudopotential formalism. In SIESTA, to construct the pseudopotential, we use atom program, which can obtain the pseudopotential solving the Schrödinger equation or Dirac equation for an isolated atom. In doing this, we obtain radial functions for each L quantum number, as we can see, for example, in this figure of of the aluminum pseudopotentials. These two curves represent the radial functions for each L quantum numbers. Instead of solving the Schrödinger equation, Atom can also solve the Dirac equation, and in this case there would be, for each L quantum number, two states. For example, for gold, on the right side, each L state are now split in two curves, L plus 1/2 and L minus 1/2. These two radial functions are not given directly by Atom. Instead, they are given as a linear combination, and they are called in the PSF files V down and V up. In the scalar relativistic case, without the spin orbit coupling, the term of the Hamiltonian that represents the pseudopotential is defined as in this equation for VPS. But in the relativistic case, we have to replace this operator for the one completely relativistic, being now VPSJ, the radial functions that I have described previously in a previous slide. The way to separate them is undoing the linear combination, having then the two L plus 1/2 and L minus 1/2 radial functions ready to be used to construct the pseudopotential operator, in which all the relativistic corrections are included: Darwin, velocity correction, and spin orbit coupling term. So one important thing to notice is the speed of calculation in SIESTA if you include the spin orbit. This is due to the modification of the pseudopotential term from its semi-local form to its fully non-local form of Kleiman-Weilander type. Practically, this means that instead of to perform 3 center integrals, these are factorized in products of 2 center integrals, being much faster the calculation. If some of you want to know in more detail the mathematical formalism, you can read the paper that we have published in 2012. One of the most important things when you perform a fully relativistic DFT calculation is that you can obtain the total self-consistent energy for different orientation of the magnetization. For example, in this case, we have a cobalt platinum nanoparticle composed of 55 atoms stacked, forming L10 structure in gas phase. And we can obtain the value of the total energy for different orientations. The two scans performed here correspond to variations within the plane XZ with phi equal to 0, and the same if we have phi equal to 45 degrees. These are the blue and the turquoise square dots in the plot on the right. Okay. We observe the difference in energy on whether we have all the magnetic moments pointing along Z axis or they point along the X axis. Other scan that we can do is in the XY plane, seeing that we found an in-plane anisotropy in this case. It is important that if you are going to run calculations in SIESTA, including the spin orbit coupling, read the part of the manual in which is explained some additional flags important to have a good results and accurate results, and also to take into account the convergence of some values such as the number of K points, the mesh cutoff, or the pseudopotential generation. Finally, I want to highlight that SIESTA will give you in its output slightly different information if you include the spin orbit, as you can see on the right, where the total energy has been separated in several contributions, and also you can see here the contribution of the spin orbit coupling to the total energy. Also, it is possible to obtain the band structure, perform optimizations. You can also obtain a Mulliken analysis, a population, and calculate the magnetic moments and also the charge per orbital or per atom. And also you can calculate and obtain the projected density of states. Thank you very much for your attention.